Okay, let's dive into the pretty amazing world of machine control. We're going to explore the hidden engineering that makes massive, powerful machines go, and maybe even more importantly, what it takes to make them stop. I mean, think about it for a second. How do you actually do that? You see these giant overhead cranes placing steel beams with millimeter perfect precision, or a textile loom weaving fabric faster than you can even see, without a single mistake. How is that even possible? It feels a little bit like magic.
Well, what if I told you the answer isn't some unobtainable secret? The core principles are actually hiding in plain sight, in machines you might see every day, like an industrial sewing machine. Turns out the fundamental challenges of motion control are pretty much the same whether you're dealing with something huge or something small. At the end of the day, this whole complicated field really just boils down to two simple opposite challenges: making things move and making them stop moving. The go and the stop. Everything we're about to look at is an answer to one of those two problems. And this is really the core of it all. See, making a machine move is the easy part, but making it move with the kind of precision that modern manufacturing demands, that's a whole other story. And stopping? Well, stopping isn't just about safety. It's about quality, it's about efficiency, and it's about preventing very, very expensive damage. So let's start with the first part of the puzzle, getting things going. You've got a motor creating all this power, but you have to get that power to the parts of the machine that are actually doing the work. And how it gets there? Well, that changes everything. So you're basically looking at the two main ways this is done. On the left, you've got your classic belt drive. It's been around forever, it's simple, but that belt can stretch and slip, and that creates a tiny bit of delay. But on the right, you've got direct drive. The motor is literally bolted right onto the shaft. The connection is solid, and the power transfer is, bam, instant. And you don't have to take my word for it. This quote from a craftsman on a leatherworking forum just nails it. That phrase, a minimum of slack, that's the whole ballgame. For someone sewing leather, that instant response means a perfect stitch every single time. For a giant industrial robot, it means unbelievable precision. But, it's never that simple, is it? Direct drive gives you that incredible performance, plus it's a lot quieter. But that comes at a cost. That motor is usually a custom part made just for that machine, which can make repairs a real headache. It's a classic engineering trade-off. Although, as the cost of electronics keeps dropping, that trade-off is looking better and better for direct drive. Okay, we've got our machine moving exactly how we want it to. Now for what is arguably the more critical part, stopping it. A good brake doesn't just halt motion, it controls it. And that control is key for safety and for the quality of whatever you're making. And just like with drive systems, you've got a couple of main options. Think of hydraulic brakes as the heavyweight lifters. They use fluid pressure to generate immense stopping force, perfect for something like a giant crane. But electromagnetic brakes, they're the sprinters. They react almost instantly, which makes them absolutely perfect for high-speed, precision jobs. And here's a perfect example of why that speed is so important. On a modern loom weaving fabric at insane speeds, even a split-second delay when it stops can cause a flaw in the fabric, called a stop mark. But with a super fast electromagnetic brake, the loom stops with such precision that the flaw never even has a chance to form. You get a perfect roll of fabric every time. But stopping these incredible machines creates this invisible side effect. All of that energy, all that momentum has to go somewhere, right? It can't just disappear into thin air. That energy gets converted into heat. And we are not talking about a little bit of warmth here. In these big industrial machines, the amount of heat generated during braking is just staggering, and that creates a whole new set of problems for engineers to solve. To really get a sense of this, just think about your car. If you slam on the brakes, the surface of your brake discs can hit 1,000 degrees Fahrenheit. Now just imagine that on the scale of a giant factory machine. The physics is exactly the same, but the energy is way, way bigger. If you don't manage that heat, the machine will literally destroy itself. So how do you fight that kind of fire? Well, one really elegant solution is the heat pipe. Basically, it's this sealed tube with a special liquid inside. The heat from the brake boils the liquid into a vapor. That vapor zips over to the cooler end of the pipe, where it condenses back into a liquid, safely releasing all that heat far away from anything important. It's like a superhighway for heat. So we figured out how to get rid of the heat. That's great. But then, for decades, engineers have been asking a much deeper question. What if we didn't have to throw all that energy away? What if waste wasn't actually waste at all? And this is a really brilliant way to see that idea in action. In this concept for a sewing machine, when the operator stops sewing, the machine's momentum, which would normally just become wasted heat, is instead used to spin a tiny generator. The energy isn't thrown away, it's recaptured.
This whole idea has a name, and if you're a motorsports fan, you've definitely heard it. It's called KERS, for Kinetic Energy Recovery System. It was famously developed for Formula One racing, and it's designed to do exactly what we just saw, turn the energy from braking into storable, usable electricity. Instead of waste heat, you get power.
Now this is where the story takes a truly amazing turn. This technology, which started in race cars and giant industrial machines, is now being scaled down to a level that honestly feels like science fiction. That's right. Researchers are now applying these exact same principles to harvest energy from our own bodies. The simple act of walking, of swinging your arm, all of that generates tiny bits of kinetic energy that could be captured to power the devices we wear every day. Of course, it is not easy, not by a long shot. Shrinking a system that started in a race car down to something that fits in a smartwatch, well, that comes with huge challenges. Making it small enough is the biggest one, but right behind that is power density. Actually getting enough energy out of it to be useful. And yep, they still have to be durable and manage heat, even on that tiny scale. And this all brings us to this one final, pretty wild thought. The exact same engineering principles that stop a 10-ton loom with perfect precision could one day mean you never have to charge your smartwatch again. It's just a powerful reminder that sometimes the biggest engineering problems have a hidden connection to the smallest pieces of tech that shape our lives. So, what happens when that line between us and our technology's power source just disappears completely?